This video is super important. It links determinant properties and elementary row operations. On your final exam, especially on the multiple choice section, they'll sometimes give you matrices that look very complicated. They're not going to be diagonal, upper triangular, or lower triangular matrices, so you can't use properties on them directly. But a lot of times we can use elementary row operations to swap certain rows to make it a much nicer matrix to find the determinant of. So we have three EROs. They involve swapping two rows, multiplying a row by a non-zero constant, and adding a multiple of one row to another existing row. Let's start with swapping two rows. If you go from A to B by swapping a row, then the determinants will be negatives of one another. So determinant of A equals negative determinant of B. All right? As an example, we have this matrix here, 1, 2, 3, 4. If I swapped row 1 and row 2 and ended up with 3, 4, 1, 2, I know that the determinants will be negative of one another. This next property, in the past, I find students really struggle with this one. So let's try to clear this one up together. If I obtained matrix B from matrix A by multiplying a row in A by this constant C, then C times the determinant of A will give me the determinant of B. Now, in the past, the most common mistake or the most common confusion is, where does this C belong? Does it belong with the determinant of A or the determinant of B, or is it 1 over C? All these different variations. My trick to you is this. I am multiplying A by C. I'm multiplying a row in A by C to end up with B, right? It's a row in A times C that gives me B. So it must be determinant of A times C that gives me B. All right? The multiplication stays the same. Multiplying a row in A by C, I need to multiply the determinant of A by C. So as an example, I started with the matrix 1, 2, 3, 4. If we multiply row 2 by 2, so here notice that 3, 4 became 6, 8. That means I have to multiply the determinant of this smaller matrix by 2 to get the determinant of the bigger numbers in that matrix. Okay, so again, the smaller numbers, 3, 4, became the bigger number, 6, 8. So I need to multiply the smaller number by 2, the determinant of these smaller numbers. All right. Next up, we have adding a multiple of one row to another. This one's super nice. Okay, we dealt with the difficult one. This one, if you're adding a multiple of one row to another, the determinant stayed the same. So for example, notice that I started with 1, 1, negative 1, negative 1. If I changed row 2, so in this case, my row 2, I added row 1, it became a 0 row, my determinants don't change because I didn't multiply a row by a non-zero constant. I added a multiple of one row to another. Really important now. This is the only time that EROs are actually ECOs as well, okay? What I mean by ECOs is they're not just elementary row operations, they are elementary column operations as well. So all three of these determinant properties hold even if the operations are performed on the columns instead of the rows. So for example, we know that swapping two rows will result in a negative determinant, right? Negative of the original. Swapping two columns will also make the determinant negative of the original. Multiplying a column by a non-zero constant, this second property will still hold. Adding a multiple of one column to another column, this third property will still hold. But do not mix columns and rows. So do not switch a column and a row. Do not add a multiple of a row to a column, okay? You can only deal with columns and columns or rows and rows. That's it. Let's find the determinant of this 4 by 4 matrix A. Now, on the final exam, whenever you see a bigger matrix, like a 4 by 4, 5 by 5, and so on, I highly recommend trying to use properties instead of finding the determinant directly. Yes, of course, you can find the determinant directly using what we know, but using properties makes it a lot easier. This guy isn't too bad because we have a 0 column with a single number 1. So if you wanted to, you could find the determinant along this column and it won't be too messy. But let's try to use some properties here. I see a lot of zeros, and what I'm going to do is try to make this into an upper or lower triangular matrix. I'm actually going to try to make it upper triangular because it's the same procedure as making it into RREF. So I have matrix A. I want to make it upper triangular, meaning sort of RREF. I'm going to bring this 1 up top so that I get a leading 1 in my top left corner. So I'm switching row 1 and row 2. We end up with this matrix with the 2 rows swapped. Now I have a leading 1 with a bunch of zeros below, so that's good. Now I need another leading 1 right there. So I'm going to swap rows 2 and rows 4. Now I'm super close to an upper triangular matrix. For me to get to an upper triangular matrix, I need to make this guy 0. So I'm actually going to just subtract row 4 and row 3 there. So my row 4, I'm going to get by subtracting row 3. Now this guy is an upper triangular matrix. The determinant is nice to find. I'm going to call this B. So I know how to find the determinant of this last matrix, but I did a bunch of EROs, and I don't want to mess up my process here when I'm dealing with EROs. So what I'm going to do is I'm going to label these guys A1 and A2. And let's work backwards to figure out what the determinant is. All right, so determinant of B, working backwards, is going to be the same as the determinant of A2, because remember, adding or subtracting a multiple of one row to an existing row doesn't change the determinant. So these guys are the same. Well, how about A2 and A1? Well, A2 and A1, the only difference is that I swapped a row. Swapping a row makes it the negative determinant. Okay, so instead of determinant of B equaling determinant of A2, it's the negative of determinant of A1. And how is that related to A? Well, that's another row swap. So I have negative of negative determinant of A. Okay, because a row swap makes it negative. So simplifying this chain of determinants, I know that the determinant of B equals the positive determinant of A. Well, determinant of B is super nice to find. It's upper triangular. So the determinant is 1 times 2 times negative 1. Which gives us negative 2. So that means that the determinant of the original matrix A is negative 2. Whenever you're performing EROs, I highly recommend writing out every step and then working backwards so that you have a chain of determinants. That way you won't miss any multiplications of negatives or constants.